All right, let's jump in. Hope everybody's had their coffee this morning. We got a lot of great stuff to talk about today. We're going to be focusing on industrial electrochemistry for the profitable decarbonization of chemicals. Okay, so who are we? My name is Mike Ashley. It's great to have everybody here today, so thank you again for joining. I'll start this presentation at a high level talking about the decarbonization of the chemical sector and where that is starting. And of course, everybody's heard of the clean hydrogen boom that's going on right now. So we'll start there. And I work really on the business side of our company, Mattiq. And then joining me is Jordan Swisher. And so he'll be diving a little bit deeper into the details on the engineering of electrochemical systems and these applications beyond hydrogen that we'll be talking about today. And he works on the technical side primarily at our company. And so we are Mattiq. We are based in Chicago in the US and are working to solve many of the challenges that we'll talk about today. And so I'd just like to say before we get going that I've dropped a link in the chat. If you'd like to set up a meeting with me or Jordan, please click on that link and feel free to sign up to put time on my calendar. So who's in the audience today? We've got C-level industry executives, investors, R&D folks, BD folks, engineers, graduate students. So this is, of course, a pretty diverse audience, and we're excited and hopefully can give a little bit of something for everybody here today. But of course, we both come at this problem from really a technical angle, but we'll talk a little bit about economics and value drivers of electrochemistry as well, and how we think this can enable a profitable decarbonization of chemicals. So what do we want you to get out of this? Decarbonizing chemicals, major opportunity. Chemicals is a massive sector of the global economy, and transitioning away from fossil fuel feedstocks and fossil fuel heat towards a renewable and clean chemicals business is a major economic opportunity. And so this begins with clean hydrogen, quite a bit of investment going into clean hydrogen today, as I'm sure everybody is well aware. But that is really just the beginning of what is possible with industrial electrochemistry. If there's one takeaway we'd like you to take from this webinar, it's that clean hydrogen is just the tip of the spear. There is so many more things we can do with electrochemistry besides just water splitting into hydrogen. And finally, of course, economics are king, but electrochemistry offers unique operational benefits that add value, not just from a cost perspective. And we'll get into what that means with some of Jordan's case studies towards the end of the talk. And so what's the agenda? I'll start at a high level talking about how we can decarbonize chemicals through electrochemistry, beginning with clean hydrogen. And then Jordan will dive more into the details of industrial electrochemical systems beyond hydrogen and what value those provide to chemicals producers. And finally, he'll be talking about how do we overcome bottlenecks to scale for each of these technologies? How do we take technology development, overcome some of the key bottlenecks that are preventing them from being operationally successful and economically valuable, and taking those to scale such that we truly can decarbonize chemicals. And finally, we'll wrap up with Q&A. So please feel free to drop questions in the chat anytime throughout this presentation. Okay, so we'll start with a little discussion about some of the hard to abate sectors of the global economy. And this, of course, has become a term of art. And honestly, we take it as a challenge. And so there's some great work that came out actually earlier this week from the Iridium group and then reported by Canary Media, both of which companies do phenomenal work in this space. And so this was also very timely for us as we'll be talking about industrial decarbonization today. So what are we looking at on the left-hand side of the screen here? These are US carbon emissions by sector as of 2022, and then transitioning to 2035 under a business as usual scenario. So that is technologies that are commercially attractive and available today that would decarbonize these various sectors. And so if you look at the status today, transportation is the greatest emitter in the US economy. followed by industry and power generation, and then agriculture and buildings a bit lower. And so what this plot shows us is that transportation and power generation, the decarbonization of those sectors is well underway, and we have a very clear line of sight towards decarbonizing both of those sectors in a very significant way, especially power generation, which is anticipated to realize at least a 67% reduction in emissions by 2035, with transportation at a 24% reduction under this business as usual scenario. However, industry remains unchanged as there aren't attractive and commercially available decarbonization solutions for industry today. And so by 2035, industry can become the biggest US climate problem, to quote Canary Media. And what does industry mean? So primarily in terms of carbon emitters, this means cement, steel, and chemicals. And arguably chemicals would be the trickiest of these three to decarbonize because there's so many different chemicals out there that need to be decarbonized. And so how do we go about decarbonizing the chemical sector given that challenge? And so that's what we'll be focusing on for the remainder of today's presentation. So global economies and governments are really starting to rally around clean hydrogen, where we can start with water and electricity to split water into its constituent components, oxygen and hydrogen. And so really, what's the background here? Hydrogen is used primarily as a chemical feedstock. About 100 million tons of hydrogen are produced per year. And nearly all of that comes from steam methane reforming, which produces about 10 tons of CO2 per ton of hydrogen produced. And so given that metric, it's no wonder that if we wanted to start with one thing, get that right and solve it, to really solve a broad swath of decarbonization in the chemical sector, this is the perfect place to start. So water electrolysis today is getting quite a bit of investment in both the manufacturing, but also the deployment and operation. So we collectively are starting to get very good at manufacturing, operating electrochemical reactors in the form of water electrolyzers. So what's the status of this industry right now? And in Jordan's half of the presentation today, you'll be seeing more plots like this, which talk about the state of electrolyzer or electrochemical reactor development for various technologies. And so really what I'll say here is that water electrolysis technology is fairly well figured out. There are some kinks yet to be worked out in terms of operation, deployment, things like grid integration, to make sure that we really know how to operate these things over long periods of time and getting clean, affordable, renewable power to run them. But you'll see that we've added this red dot here on the catalyst part of this analysis. And really what this signifies is that catalyst materials can really be a bottleneck to scale in the deployment of water electrolyzers. And specifically what we're referring to here is Iridium. So Iridium is the state-of-the-art anode catalyst in PEM water electrolyzers. And the reason it's the state-of-the-art is because it's the only known material that can hold up under the very stressful, acidic, and highly oxidative conditions of PEM electrolyzers. The problem arises because there is a very large mismatch between the amount of iridium that's available for PEM electrolyzers every year, say 1 to 2 tons in total across the globe, and the amount that is forecasted to be needed for 2030 projections for PEM electrolyzers. And before that demand has really kicked in, iridium already costs about $5,000 an ounce. So this is posing a both cost and supply chain constraint towards the scale of PEM electrolyzers. And so again, we take this as a challenge and see this as an opportunity to work around this bottleneck such that PEM water electrolysis can achieve scale. And what does that mean for us as a company? We've taken the opportunity to evaluate a comprehensive design space of mixed metal oxide catalysts that have reduced or eliminated iridium content. And the objective here is to identify compositions of materials that are optimized for performance and that means both activity and the durability of the catalyst material, and cost against that state-of-the-art iridium oxide. And so I'd like to quickly summarize some work that we've done over the past couple of months. Really over a short period of time, it was really about 6 weeks of experimentation. We generated over 6 million data points describing huge materials design spaces comprised of 21 bimetallic material spaces and 14 trimetallic material spaces, identifying quite a few, several hundred materials that are as good or better than iridium oxide. And what does that actually mean? Again, that is both activity and durability. So holding up as well over long periods of time as state-of-the-art iridium oxide. So that's all I'll say on this topic here, but please reach out to us if you'd like to hear more about our work in this space. Okay, so where do we go from here? We set this up by talking about the chemicals sector as a whole, and by saying that there's a lot more that we can do besides just clean hydrogen production. If we want to think about systematically decarbonizing the chemical sector, there's a lot more that we need to think about. And so chemicals today are responsible for a bit over 6% of global carbon emissions. And this comes both from the feedstocks used, but also the fuel. And so this is what makes chemicals particularly tricky, is that it is very intricately tied to the fossil fuel industry because the feedstocks we use are almost always fossil fuel derived. And then on top of that, we need additional fossil fuels to run these processes to make, say, high temperature, high pressure processes. So we need a lot of fossil fuel to run these processes as well. And so there's a few strategies we can use in order to systematically decarbonize chemicals. And that begins with, can we source the feedstock from renewable resources? And of course, that is always part of our design consideration as we think about the next generation of clean chemical productions. After we ask that question, we ask, can the process be done electrochemically? So that is, can we drive this chemical transformation using electricity instead of heat? And that offers very significant climate benefits, as we're starting to see in the clean hydrogen space. If the answer is yes, we're going to do that. And we're going to design and optimize a system that can run this reaction electrochemically. If not, then we need to ask, what really is the source of greenhouse gas emissions in this chemical transformation? Is it coming from the heat? In which case, we can devise systems where that heat is derived from either electricity, or if higher heat or higher temperatures are needed, hydrogen heating systems are currently under development as well. And finally, if there are direct emissions from a chemical process, that is, CO2 is a direct byproduct of some chemical transformation, there's something else we need to think about, and specifically, carbon capture and sequestration becomes a very important part of the equation for those processes. So for the purposes of the rest of today's presentation, we're going to focus squarely on electrochemical process development. And so how do we think about that? Like I said on the previous slide, really what we're trying to do is put clean electrons to work as reagents in chemical processes. And if we do that, electrochemistry becomes a very versatile route to decarbonization. And I use the word versatile to say that there are quite a few reactions that can be very effectively designed by electrochemical reactors. And so by doing that, we can start to very systematically decarbonize various chemical processes. And like I said at the top of the meeting, electrochemistry offers us operational benefits besides pure cost cutting. And specifically, what I'm referring to here is, one, the use of benign conditions. And so this can mean a couple of different things. This is both avoiding sometimes extreme temperatures and pressures that you see in conventional thermal processes, but also avoiding some nasty reagents. Think things like cyanide or bleach that can be used in some chemical processes. And these things can be avoided by running electrochemical reactors, which operate typically near ambient conditions. Next, we have this concept of decentralized chemical production at the point of use. This isn't valuable necessarily for every single chemical product out there, but in some cases, chemicals have very inefficient supply chains, which, in particular for dangerous or corrosive or explosive chemicals, it would be much more valuable to produce that chemical where it is needed instead of needing economies of scale at some very large centralized facility and then transporting that out to the world where it's needed. So a very interesting benefit of electrochemistry there. And finally, what we'll get into on a few of these case studies is selective transformations. So think things like partial oxidations, partial reductions. We can make exactly the chemical transformation that we want in a selective way without, say, over-oxidizing or over-reducing some chemical feedstock. And this, of course, has significant implications for purification downstream as well as your overall feedstock utilization. So, yeah, I've alluded to this a few times, and I hope this slide isn't too scary, but really, I want to communicate here that there is a very large universe of possibilities for electrochemical transformations that we can develop and deploy into the field. And those are depicted on the right-hand side of the screen. These are chemical transformations that have been demonstrated to be done using electrocatalytic reactors. And so we can't do all of these at once, of course, and so we need to prioritize from this universe of possibilities. And we do that by asking some very key questions up front. What are the economics of these processes? Do they work without incentives? What does the status quo process look like? Are there very acute pain points in this process, say the use of very harsh chemicals like bleach or cyanide? And finally, how significant are the environmental benefits? Again, this isn't just carbon emissions, although that is a very significant part of this equation. This is also the use of regulated or dangerous chemicals that we can avoid using electrochemical processes. So where does this lead us? Where do we look? There's a few ways we can think about attacking this sector. And really, if we think about what is next after water electrolysis, a lot of folks will say that CO2 electrolysis is a very attractive and good fit for what's next. And indeed, say CO2 conversion into ethylene is a very attractive route to decarbonizing a very wide array of hydrocarbon chemicals, as ethylene is the largest chemical market in the world and used to make quite a variety of different end product chemicals. However, if we dig into the economics a little bit here, we quickly run into a challenge where the electricity demand for that you would need to make this transformation exceeds the market price of ethylene. And so, this leads us to this first economic challenge as we think about prioritizing different reactions. And we need to think about what needs to be done in order for this process to become economically attractive. And so first, we need to affect a step change in the CapEx of these systems, such that we can then chase cheap and most of the time intermittent power. And so what I mean by this is, think about a utility scale solar facility, for example, operates about 30% of the time, but gives you very cheap, clean power. And so if we can reduce the CapEx such that operating at a low capacity factor becomes viable, then this process starts to look a lot more economically attractive. And of course, government incentives will help here as well, as, like I said, making ethylene from this renewable CO2 could decarbonize a very wide array of end product chemicals. But we're not going to focus the rest of this presentation on that particular reaction. We're going to choose a few different ones to look at instead, where we think the economics are quite attractive given proper system optimization and development. And so the first application I'll highlight here is a hydrogenation process in the value chain for nylon, which is one of the most ubiquitous engineering plastics in the world. And so what you can see we've done here is looked at the market price of this product, compared against the estimated electrochemical production costs, And that cost is inclusive of not just electricity, but fully loaded with feedstock costs, purification, O&M, labor, et cetera. And so with a properly optimized electrochemical system, this is one application by which electrochemistry offers a number of benefits. And this is not just cost. Again, there's this unique operational advantage we can achieve with electrochemistry. And specifically, I'll tie this back to our three bullet points from the previous page. And this one would be the use of benign conditions. And Jordan will get a bit more into what that means. Next, Jordan will tell you about another application, the oxidation of ethanol to acetaldehyde. And again, we can look at the market price of that chemical with its electrochemical estimated production cost. And again, we can see that we can beat that market price with sufficient margin in order for these processes to be economically attractive for investment. And acetaldehyde is a highly corrosive chemical. And so this is something that would be appropriate for this decentralized production value driver, where producing that chemical at the point of use in the correct quantities is a very attractive value driver of this electrochemical system. And finally, Jordan will wrap up with a discussion of the semi-hydrogenation of acetylene to ethylene, where the primary use case of this electrochemical system would be for the purification of ethylene streams, which typically have this acetylene contaminant within it, which needs to be removed before polymerizing your ethylene into polyethylene, because that acetylene contaminants can poison your downstream catalyst. And so this is a very important, very high volume process. And again, this is something that electrochemistry is uniquely suited to deliver on, as you can affect a selective hydrogenation of acetylene to ethylene without over-reducing it to ethane. And so Jordan will dig into the details of that as well in the coming slides. So with that, I will hand it over to Jordan to take you through these case studies in a bit more detail.
Yes, thank you, Mike. And for the next couple of slides, what I'm going to do is I'm going to take a deeper technical dive into the three applications Mike just highlighted and really address the key technology bottlenecks, or in our view, the challenges, the technological challenges that are limiting the commercial implementation of these technologies. And now, I'll say there are, of course, many related technology challenges to overcome in some of these applications. And we're going to highlight the ones that we see as the most critical to solve to move these technologies into the industry. And so we'll start with avoiding harsh conditions with electrochemical hydrogenations, specifically the hydrogenation of a diponitrile to produce HMD, or hexamethylene diamine. Now, for some background, nitrile hydrogenation, and specifically a diponitrile hydrogenation, is a critical step in the production of nylon 6,6. But in industry, it requires harsh conditions such as elevated temperatures and pressures, and either hydrogen or supercritical ammonia feedstocks. Now, this set of conditions is it's preferable to avoid high temperatures, high pressures, and reagents such as supercritical ammonia. And so our solution, as we see it, is a selective electrochemical hydrogenation run at near ambient conditions. And so you can see in the bottom left-hand side of the slide, this is a cartoon of what an electrochemical reactor might look like, wherein a diponitrile is hydrogenated at the cathode within an electrolyzer. Mike, could you take me to the next? There we go. And so this will bring this plot back up. And for each of these unique applications, we'll give you our estimates on where these technologies lie on the electrolyzer development pipeline. And so right away, you can see we view this technology as far less mature than PEM water electrolysis. Of course, it's very early stage development. But what I want to point out is the key critical bottlenecks as we see it, which are highlighted in red, which include, in this case, reaction conditions, membrane and mass transfer or mass transport. And so on the next slide, I'll touch on some more details as to why that's important as we look to implement these technologies at scale. And so first of all, adiponitrile has a limited solubility in aqueous electrolytes. Most electrochemical reactors operate in aqueous-based electrolytes, and organic solvents can be used to increase the solubility of adiponitrile, yet organic solvents can oftentimes reduce the electrolyte conductivity and may have deleterious effects or unwanted side effects on membrane properties and electrode properties. So the opportunity in this case, as we see it, is to develop and engineer an electrocatalytic system that operates at near ambient conditions in aqueous-based electrolytes, which does not require hydrogen gas or supercritical ammonia. And I'll just highlight a few examples from the literature that show the current state of the art with this technology. So on the right-hand side of the slide, we have examples on the top from Miguel Monastino at NYU. And their group is doing a lot of really great work in electrosynthesis. And in this case, they were actually looking specifically at adiponitrile hydrogenation. And they were testing different conditions and variables to maximize selectivity of the adiponitrile hydrogenation to yield hexamethylene diamine. And one of the main challenges, in addition, that I didn't highlight on the previous slide is selectivity for the hydrogenation of ADN and not producing hydrogen. And so what you'll see on these plots is, first of all, on the leftmost plot is testing various adiponitrile concentrations. And so what we can see here is that even at relatively high current densities for this type of chemistry, 90 milliamps per centimeter squared, the Modestino group was still able to achieve relatively high selectivities for HMD from adiponitrile. And in this case, they actually went beyond the theoretical or the solubility limit of adiponitrile, which is about 0.45 molar in water, by adding surfactants and solubilizers. And this is a very promising result, indicating that even with additional additives, they were capable of achieving high selectivities with modest current densities. Additionally, in the centermost plot is tuning the reaction temperature. In this case, we see that to reach the same current density with increasing temperature, lower cell voltages are required. And additionally, they were able to maintain very high selectivities. And then lastly, to the point I made previously about organic solvents, on the rightmost plot, they're using methanol as a co-solvent with water to increase the solubility of adiponitrile within these electrolytes. And what they see is that there's actually really, at least within the 3 electrode cell testing setup that they were using, very little, in fact, there's benefits to increasing the methanol concentration based on this data set. And the bottom plots I'll point you to are from Feng Zhao's group, where they were looking at an analogous system. So the hydrogenation of acetonitrile rather than adiponitrile. Now, acetonitrile doesn't face the same mass transport issues or solubility issues, but in this case, it's very similar chemistry, right? The hydrogenation of a nitrile functional group. And what they were testing first is various different catalyst materials, and they identified that copper is the most selective towards the production of ethylamine in this case. And they also ran electrolyzer type experiments for 20 plus hours and saw that, first of all, moderate cell potentials are required to achieve high selectivity and high turnover. And that selectivity was maintained for at least 20 hours of operation. And so really the main takeaway from this slide is that, there's obvious advantages to an electrochemical solution for this technology. And the chemistry has been demonstrated. And really the challenge is now is balancing current density or turnover rates, as well as additives and the potential negative side effects that those additives may have to increase solubility of the adiponitrile. And so this is just really highlighting some of the key challenges in commercializing this specific technology. And it's unique from the next two case studies that I'll go into. So next, we're going to talk about and highlight an application that's emblematic of Mike's second point, which is modular and distributed production of chemicals for production at the point of use. And the example we're gonna stick with here is the ethanol oxidation to acetaldehyde. Now, Mike mentioned this already, but acetaldehyde is a corrosive chemical, which is expensive to transport safely. It has a very high vapor pressure. And currently, acetaldehyde is produced from fossil-sourced ethylene through the high-temperature oxidation of ethylene. And so, of course, it would be better if we could produce acetaldehyde from renewable feedstocks. And so our proposed solution is to produce acetaldehyde in right-sized reactors at the point of use from renewable feedstocks, such as bioethanol. Now, again, we can look at the electrolyzer development pipeline chart that we've showed a couple times now. But I suppose before I move on, one thing I want to highlight here is on the bottom left side of the slide, there's again a cartoon of the electrolyzer. And what we see here is that since we're doing an oxidation, in this case, the cathode will also be producing hydrogen. So not only can we produce or upgrade ethanol, but we can also produce hydrogen, which is a real advantage of many organic oxidations. And so looking at the maturity of this technology, we can again, we filled this chart out with our estimates of the current state of the art. And we see that, again, the maturity is quite far from PEM water electrolysis. But the key bottlenecks in this case are slightly different than the previous application, where reaction conditions, catalyst materials, and again, mass transport are the things that really need to be figured out for this technology to be brought to commercial viability. So the key bottlenecks to scale are engineering electrolyzers that are selective for the production of acetaldehyde versus other products. And I'll touch more on that in just a moment on how the selectivity is determined and how we can potentially optimize and engineer the selectivity of these reactors. And then second is required feedstock purity. So it's unclear what the required purity of ethanol as an input stream is for electrolyzers for ethanol oxidation. And the reason why that's important will become clear here in a moment. And so the opportunity as we see it is to produce clean acetaldehyde from biosourced feedstocks and renewable electricity. So bioethanol, renewable electrons to produce acetaldehyde. Additionally, this type of technology presents an opportunity to make product or make acetaldehyde from dilute and potentially even impure ethanol in water or aqueous-based solutions to simplify purification. So I'll dive a little bit deeper on that. So ethanol or dilute ethanol in water is a fairly common waste stream, and it's to purify the ethanol from aqueous solutions is quite energy intensive due to the similarity in boiling points of ethanol and water. And so if we could take ethanol or dilute ethanol streams in water, oxidize that ethanol to acetaldehyde, which has a much lower boiling point, we can not only increase the value or upgrade the value of that ethanol by making acetaldehyde, but we can also massively simplify the purification due to the very low boiling point of acetaldehyde. And potentially this could be used for even impure streams of ethanol, depending on the purity required for an electrochemical system such as this. And then lastly, to unlock on-site production of acetaldehyde. And this can be used for a myriad of different applications, such as on-site solvent production, as an example. And so just to dive just a little bit deeper into the chemistry, on the top right of the slide is the mechanism of the ethanol oxidation reaction. And in papers, you'll see a little bit of a few differences here and there between the mechanism, but generally speaking, it goes something like this, where The ethanol is deprotonated and adsorbed to a catalyst surface. And that adsorbed intermediate can either undergo the 2-electron oxidation to acetaldehyde, or a subsequent oxidation totaling 4 electrons to make acetic acid, or it can undergo a complete oxidation to carbon dioxide. Now, there's, of course, a reasonable argument to be made that either acetaldehyde or acetic acid are valuable products and higher value than ethanol. But if we want to select for the production of acetaldehyde, this is going to be in part a catalyst optimization problem, where we need to find catalysts that are selective for that 2-electron oxidation to produce acetaldehyde. Another thing I'll note, and on the bottom right side of the screen, is that the selectivity is a bit more complicated than just the electrocatalyst selectivity. And in this case, there's an additional series of steps that can happen that change the selectivity of an electrolyzer for ethanol oxidation. And so apart from the electrocatalytic selectivity, which is on the top right, there's also chemical selectivity, and that's on the bottom right side of the slide. Now, in an electrolyzer, acetaldehyde is highly reactive and can actually react with ethanol in that reactor. And there's been literature demonstrations in, for example, AEM membranes where the pH is very high, where the main product is actually ethyl acetate. Alternatively, if we're using a proton exchange membrane where the pH is quite low, and there's been additionally demonstrations of the production of 1,1-diethoxyethane. Now, these very well may be products of interest and something worth optimizing for, but if we're trying to produce acetaldehyde, we need to take this into account. So not only the catalyst, but also the reaction conditions, as well as the mass transport within that electrolyzer. And so I mentioned the boiling points previously, and I noted the boiling points here on the slide of both ethanol and acetaldehyde. And you'll notice that the boiling point of ethanol is much higher than that of acetaldehyde. And so it's feasible to envision an electrolyzer or an electrochemical system which operates at elevated temperatures, and upon the production of acetaldehyde, it actually evaporates out through a gas diffusion electrode or something of the like. And in that case, we could potentially limit any further oxidation or further chemical reactions with acetaldehyde, thereby increasing selectivity towards acetaldehyde. And so that's really a summary of the key challenges and bottlenecks for this particular application. And next, we'll move on to the last one, where we want to reduce product loss in the purification of ethylene. And so by way of background, ethylene is most commonly produced via naphtha cracking. Naphtha cracking oftentimes leads to, in every case, leads to at least some amount of acetylene in the product stream. Now, acetylene is a catalyst poison for the subsequent Ziegler-Natta polymerization to produce polyethylene. And so to produce polymer grade ethylene, there must be the suggested amount of acetylene is about 1 ppm. And these product streams after naphtha cracking can have as much as 10% acetylene within these product streams. So the acetylene must be removed by semi-hydrogenation. That's the current method used in industry. Now, semi-hydrogenation is effectively hydrogenating acetylene to ethylene in the presence of ethylene. But the current process has issues with selectivity. In many cases, you'll make ethane and you'll over-hydrogenate both acetylene and ethylene. Other harmful byproducts such as coke and green oil or oligomers of ethylene and acetylene can be produced during this process, which leads to catalyst durability issues. And this current process requires additive hydrogen and, in fact, carbon monoxide, which is used as a catalyst poison to limit the overhydrogenation. And so our proposed solution is to develop an integrated electrochemical acetylene semi-hydrogenation unit powered by renewables. And so again, if we look to the electrolyzer development chart, this one looks a little bit more mature. And now there's a handful of examples in the literature, and this chemistry looks really quite promising. So we've bumped up the maturity of this process. And we want to highlight a slightly different technological bottleneck for this particular application, which is integrating this process or a new process into an already existing a larger chemical plant presents its own set of complications and challenges, which need to be thought through if these technologies are going to really be brought to scale and implemented in industry. So the bottlenecks include a complex reactant feeds. So from a naphtha cracker, the reactant feeds or the product streams can include variable amounts of ethylene, acetylene, hydrogen, carbon monoxide, and light hydrocarbons. And these can vary depending on plant operation. And additionally, the pressure of these product streams is typically about 15 to 35 bar in most industrial processes. So looking to the opportunity, we see the electrochemical semihydrogenation of acetylene as an opportunity to reduce ethane waste or limit overhydrogenation, reduce coke and green oil formation, or the production of harmful byproducts by creating a more selective electrocatalyst system, and entirely eliminate the need for hydrogen or CO addition. And additionally, one thing I'd like to highlight is potentially unlocking a renewable pathway to ethylene. Now, there's been some recent work on the production of bio-sourced acetylene using biomass gasification in plasma arc reactors. So biomass in a reactor that's powered by renewable electricity to produce acetylene. Now, if we can then take that acetylene and hydrogenate it to ethylene, we now have a completely renewable source of ethylene, which of course is one of the largest produced chemicals by volume in the world. But if we dive into the current state of the art, the initial demonstrations of this technology look extremely promising. And so here's some snapshots from a paper from earlier this year in which this group was actually using an electrochemical semihydrogenation of acetylene in the presence of ethylene to try and simulate these gas mixtures which are produced in via naphtha cracking. And what we can see is that selectivities are oftentimes well above 80% or higher. And in this case, they were testing the flow rate as well as current densities. And what we can see is that conversion and selectivity is extremely competitive with existing thermal processes for the semihydrogenation. And additionally, in this paper, they also performed long duration stability experiments for over 120 hours. And these electrolyzers can be operated at modest cell potentials and yield high turnovers, high conversions, as well as minimal byproducts such as hydrogen and oligomers such as coke and green oil. And so this technology is a bit different, and this application is a bit different than the other two, where the real, one of the major bottlenecks is going to be integrating this into an already existing chemical plant, right? How do we displace an existing technology with a new and emerging application? And so that brings me to the conclusion of the webinar, where I want to talk just a bit on the path forward and really stick with the theme of bottlenecks. So we talked about bottlenecks for green hydrogen and some of these newer applications. And I want to think about some of the bigger picture bottlenecks for the implementation of these technologies. What's keeping us from making these technologies happen? And so I'll highlight just a few points that I really want to spread out into this field and amongst the audience today. And so first is technology collaboration. And so the first point under that bullet is connecting what is possible to what is meaningful. And what do I mean by that? And this is a point that I make all the time. And Mike showed a slide a few slides back that highlighted the types of chemistry that are possible with electrocatalysis or with electrosynthesis. Now, we see lots of demonstrations in the literature, and we know that there are many different types of chemistries that are possible, but what is meaningful to the chemical producers? What are the pain points for those in the industry? And connecting those dots, I personally am very convinced that there are hundreds of applications out there that we may not be aware of, but once we see the chemistry, it may, a light bulb may go off and say, we can absolutely do that using an electrochemical system. And so really connecting what's possible to what is meaningful within the industry. And then second point here is attacking all stages in the development pipeline in parallel. So from the very bottom of the development pipeline, all the way up to the operation and other larger scale considerations, it's really important and will lead to the highest chance of success if we optimize all of these things with the end user in mind, or the end set of conditions in mind. Next point I want to highlight here is government funding and policy. And so first bullet under that point is bolstering support from the relevant agencies, most notably the DOE. And so we've all seen the DOE publishing reports and FOAs on green hydrogen and ways of decarbonizing chemicals production, but I have yet to see a really big effort or focus on the specific topics that we've discussed today. And so raising awareness and increasing support from relevant agencies is something that's on top of mind for us. And then subsequently leveraging existing programs to make these technologies come to life from all stages. So from the early stage, funding through the Industrial Efficiency and Decarbonization Office, from mid-stage to the Office of Clean Energy Demonstrations, and late-stage deployment through the Loans Program Office. The last point I want to make, and then we can move on to Q&A, is a shift in mindset. And this is really an industry-wide issue or call to action, right? Where the opportunity for this technology to make a difference is going to require major players in this space to adopt new and competitive technologies. And additionally, investing early can really limit the switching costs down the road and can increase the likelihood of commercial success for all of these technologies. And so really a shift in mindset, thinking to the future, how can we decarbonize the chemicals industry 10 years, 20 years from now? What are the technologies that are going to be critical for that? And so with that, I'll go through just 3 key takeaways from the webinar from Mike and I today. And first of which is the opportunity. I think we've made the case that profitable decarbonization of the chemicals sector is possible. Now, how do we get there? We see electrochemistry as a viable route to profitably decarbonizing the chemicals industry and realizing that electrochemistry can do much more than just produce hydrogen. And lastly, our vision. How can we address the key bottlenecks? How can we as a community address key bottlenecks towards the production of clean chemicals at scale? And really identifying and addressing those bottlenecks is critical at an early stage. And so with that, I will thank everyone for tuning in today. And we will be sending out a recording of the webinar via email. So if you don't get that, please reach out. And we would also really love to follow up and get your feedback on this presentation. And last point is, let's work together to solve this problem. Let's build out the economic cases and the technology cases for the industrialization of electrochemistry and how we can put renewable electrons to work to decarbonize the chemicals industry. And our contact info is on the slide here. And lastly, we are hiring, so please reach out. And yeah, with that, I'd love to transition to Q&A.
Yeah, thanks, Jordan. So thank you everybody again for participating today, and don't be shy with questions. So if there's any burning questions you have, please feel free to drop them in the chat. Otherwise, feel free to set up a meeting. There is a link posted in the chat as well to set up a meeting directly with me, but our email addresses are on this slide as well. So please take them down and reach out to us if you have any questions or want to talk through anything. So that can range from a number of things, from talking through the technology to telling us why we're wrong about various things. But we want to hear from you regardless. Okay, so with that, we've got a question here in the Q&A, and this may be a question for you, Jordan. So when performing a cathodic reduction, such as adiponitrile hydrogenation, how much does the performance of the anode impact overall performance? And can the anode be the real cost limiter?
Yeah, that's a very good question. And so the anode is always going to be critical for the overall performance of all of these electrochemical systems, especially when you're doing a reduction, for example, ADN hydrogenation. So the anode is always going to be a major factor. And really, depending on the pH, whether it's an alkaline or an acidic condition, that can really drive costs. So if you're operating under acidic conditions, then you have to rely on catalysts that Mike touched on before, which are stable under those low pH and oxidative conditions, which can, at least presently, we're hoping to, of course, change that, be much more expensive. Now, another opportunity that I didn't really touch on is the opportunity to pair electrochemical reactions and reduce cell voltage. So, for example, the ethanol oxidation reaction can be used in place of the oxygen evolution reaction at the anode, and that can reduce operating costs and cell potentials, as well as reduce the cost of the anode catalyst. So there are strategies that can not only up your value add, but also decrease your cost that comes from the anode side.
Yeah, and one comment I'll add here is that I'm sure you noted that the connection to hydrogen from the different applications that we highlighted in these case studies, where in the case of organic oxidations, as Jordan noted, there is hydrogen evolved at the cathode where you're doing some value add oxidation at the anode. And on top of that, say for the adiponitrile hydrogenation process, that actually makes the hydrogen that you need in situ in the same reactor. And so that in both cases, what that does is reduces the amount of dedicated clean hydrogen that we need to make from conventional water electrolyzers, because we have hydrogen sort of built into these systems otherwise. Okay, next up question here. So how do you assess the bar for commercially viable performance for each individual application? Yeah, so really important question here. So there's a few things that we can do to start this process. I will say it's a collaborative effort typically. And so, we can start with just a pretty simple calculation on how much electricity is needed to drive the electrochemical transformation that we want, based on a certain set of assumptions for system performance. And we can build those in based on state of the art, as well as what we think are realistic performance targets. Electricity cost tends to be the highest operating cost for systems like these. But for certain reactions, that isn't true, actually. The amount of electricity that you need is actually fairly limited. But in some cases, the feedstock that you need is the more expensive component of the overall system. From there, what we can do is run process simulation in order to figure out effectively what our separations costs are going to be, and then also build in things like ongoing operations and maintenance costs, so replacing MEAs, and then labor costs, as well as a couple of other components, including CapEx and depreciation as well. Like I said, what we like to do is build these out completely and rigorously with chemical company, so existing producers of the chemicals that we're going after. So please reach out if you're interested in collaborating with us on running some of these techno-economic analyses. Okay, another question here. How much potential do you see in the upcoming so-called self-driving labs and using iterative, e.g. Bayesian machine learning methods for catalyst design? Maybe I'll let you tackle that one, Jordan. That's a good question.
That is a very good question. So yeah, of course I see a massive potential for self-driving labs powered by machine learning for specifically for the design of catalyst materials. And we here at Mattiq are moving in that direction. One thing I will say, though, is that there is no replacement for good, high-quality experimental data, at least yet. And so we have placed a significant amount of emphasis on high-quality experimentation, and then leveraging and building off of that high-quality experimentation using self-driving labs and machine learning models to accelerate and optimize our design of novel catalyst materials is going to play a critical role for us, and will likely play a critical role for many other players in many other domains as well. And so, of course, we see lots of potential within this space. And yeah, it's a very good question. And we, like I said, at Mattiq are moving in that direction.
Okay, we've got one more question here. It seems we'll need to we will need complex multi-element catalysts to maximize the performance of the electrochemical processes you mentioned. Most of these applications, as you mentioned, deal with unpure streams. How would the catalysts react to impurities, particularly the multi-element catalysts?
That is another very good question. And now this is, of course, very case by case. And I think the answer to this question is I don't know in most cases. And the best way to find out is to very early on in the development from the ground up with novel catalyst materials, for example, for acetylene semihydrogenation, simulating the real product streams in all phases of catalyst and reactor development is critical, so that you don't demonstrate you can do XYZ performance with a pure product stream, and then as soon as you have 1% of an impurity, your performance is in the trash. And so starting from the realistic, and this goes back to a point I made earlier, starting from the end use conditions, I think is very critical for the development of these technologies, especially in a successful and rapid way. But yeah, it's difficult to have an answer, and it will be case by case, but it really highlights the importance of starting with the end use in mind throughout all phases of development for these types of technologies.
All right, thanks, Jordan. And thank you, everybody, for your questions. And thanks again for participating here today. Looks like we're at the top of the hour. So thanks again, everybody, and look out for a recording of this webinar from us probably early next week. But thanks again for being here, and look forward to continuing the conversation.